All right, so these are for biology. These are chapter 4 notes, and we're going to do both sections here. There's two sections, chapter 1 and section 1 and section 2. The first one is called population dynamics. So we're in ecology, still in the ecology unit, and we've been talking about populations, communities, and how they interact with each other. Populations, to remind you, are groups of the same species, so like all rabbits, all mice, all bison that live together in the same area. So in Minnesota, or in Thief River Falls, or in the western part of North Dakota. And there's different characteristics that ecologists study about populations, and we'll talk about why that is, or how they're different, and how different factors can impact a population growth. So we're going to talk about population density, population growth, or distribution, and population growth rate. Those are the three kind of characteristics or things that ecologists study about populations. So first of all, population density. Here is a black bear. So the density is 1 bear per several hundred square kilometers. That would be the black bear's density. The American bison's density is 4 bison per kilometers squared inches in Yellowstone. The white-tailed deer density is 10 deer per kilometer squared in some areas of northeastern United States. So density is just the number of organisms per unit area. So you have a space, here it is, per several hundred square kilometers. Here is kilometers squared in Yellowstone, and here is in some areas of northern Minnesota. Those are the area, and population density is simply just counting the number of that certain species or population in that area. How populations are distributed is something else that ecologists find interesting, or things that they want to know. So here is bison and how they're distributed in Canada up here. They have a very uniform dispersion, okay? They plotted it, where the bison could be found in that population. So it can be a uniform dispersion or distribution, or it can be a clumped. Here is, where are we in? Oklahoma or Nebraska? No, it's Kansas. All right, Kansas, white-tailed deer in Kansas. They're clumped together in groups. So that's a clumped distribution. Or here is a random distribution of some organism, some population. What drives the pattern seen? Usually resources such as food. So here there's maybe certain grass or forested areas where the deer hang out because there's food there. And then ecologists study ranges. A species range is its distribution across the environment. A species not be able to expand its population range because it cannot survive different factors, abiotic conditions for the expanded region. So there might be only a certain area or range that population lives in. Something that's preventing it from spreading out. Okay, so now we're going to talk about factors, limiting factors that prevent a population from growing forever and ever. So these factors can be biotic, living, or abiotic, non-living, that keep populations from growing indefinitely. Something stops it from growing and growing and growing and growing forever. These factors can either be categorized into two areas, either density independent or density dependent. First, we're going to talk about the density independent factors. Any factor in the environment that does not depend on the number of members. So it doesn't really matter how big or small a population is. Density independent factors will work no matter what. It'll impact the population growth. It will stop it from growing. It doesn't really matter the size of it. So these are some examples of these factors. and they're usually abiotic. So a big weather event like a flood, like that has happened in Houston, Florida, recently in 2017, the fall. Okay, that weather event took out populations of organisms. Okay, even humans in this case, because it caused them to move temporarily. But it didn't matter how big or small the population was. That abiotic limiting factor prevented growth of that population. Another example is a fire. Fires take out populations regardless how big or small they are. Humans altering the landscape, so that can be logging or development, putting up homes, or just pollution, air, land, and water pollution. Density-dependent factors, okay, so this is a different type of factor that limits population growth, is any factor in the environment that depends on the number of members per unit area. So for that factor to work, just putting some oils on, it needs to have a dense population. Okay, so these factors are usually biotic, mean living, and they include, first one is predation. And this is a graph that shows moose in green and wolves in blue in the years, so the time span on the bottom, and the number of wolves are graphed on the left-hand side and the number of moose on the right-hand side. Here's a good example. 1970, the moose population was high and the wolves were low. Wolves eat moose, so eventually the wolves started consuming. They were the predators that ate the prey of the moose, and then the moose population went down. The wolves were high because they were well fed. Now there's less moose, so over time the wolves don't have as much to eat, so their population numbers go down. So they fluctuate. This is predation. And disease is another factor that can limit the population growth. Pardon me. The bubonic plague that took place in Europe in the late 1800s wiped out many people because bubonic plague is a disease, and in that time people were Europe were living very close together. You should know, or probably do know, that diseases spread faster if you're closer together. Like, for example, colds are more common in the winter, not because there's more flu viruses or cold viruses, but because we're inside together more. Another example of a density-dependent factor is competition. If you have a lot of rabbits, it's a very dense population of rabbits, and there's not a lot of food, they're going to compete for the food, preventing populations from growing because they're out competing each other. Parasites are another example. Kind of the same reason for disease. We'll think about lice. Sorry if that makes you itch. But if it's a dense population, things like lice spread more quickly, reducing population numbers. Not that lice kill you, but imagine other parasites that are more deadly. So, these limiting factors, whether density independent or density dependent, impact population growth. Population growth rate explains how fast a given population grows. Okay, so population can grow a few different ways. Births, that's a fancy word for saying births. Okay, if you have more of any organism being born, that's going to increase population rate. Another thing that can impact population growth rate is the opposite of this, and it's not listed. You can maybe put it in parentheses here. Deaths. If births make the population number go up, deaths are going to make the population number go down. Immigration. That is a factor that can impact population growth rate. That would be individuals that move away from a population for whatever reason. Maybe they want to go down south where it's warmer, like I do. Immigration is new individuals moving into a population that can cause population numbers to go up. So the 4 non-specific factors that affect growth rate: birth and death, and immigration, and emigration. One of the first type of graphs that I want you to know about is the exponential population growth. Over time, we see the months here on the x-axis, and then mice population in millions. Okay, so exponential growth is when growth is slow to start out, but then increases at a rapid rate. This is called exponential growth. All populations grow exponentially until they encounter some kind of limiting factor. Those factors that we just talked about: disease, competition for resources, etc., that prevents them to continue growing exponentially. Then I'll bring you to the next type of graph that you need to know, called a logistical growth model. This is more common in nature because usually a limiting factor will prevent exponential growth forever. Oh, there goes the lights again. Okay, so here it is. Occurs when a population growth slows, so right here, or stops following exponential growth. So again, the beginning of the graph looks exponential. Okay, growth is slow to begin with, but as more individuals go into a population, growth is exponential. But then something is slowing down that growth or even stopping it at a little steady state right here. Okay, and this level that growth stops at, or that hovers around, it's called the carrying capacity. Carrying capacity is the maximum number of individuals that a particular environment can support. So what stops growth from happening? Well, the number of births needs to be less than the number of deaths, or emigration, people leaving, or individuals leaving, needs to be higher than immigration. Again, carrying capacity defined for you is the maximum number of individuals in a species that an environment can support. So depending on the species, depending on the environment, carrying capacity can differ. Just think about it. One environment could have plenty of food to eat. One could have not enough to eat. Each different environment is going to have a different carrying capacity for every number of individuals. Something interesting to note about populations. Populations, different species, differ in their reproductive patterns. They differ in the number of births per reproductive cycle, in the age the reproduction begins, and in the lifespan. So do humans usually just have one birth per reproductive cycle? Other organisms like pigs, for example, have a lot of piglets per reproductive cycle. Age the reproduction begins. Humans, teenage girls, sometime in late grade school, usually middle school though, right?